Unit 6.4, Shear Flow in Built-Up Members. In this unit, we have focused on the course outcome, demonstrate the ability to calculate normal and shear stress and deflection in beams. In this lesson, we will focus on being able to calculate shear flow and fastener spacing in built-up members. Let's begin by considering this beam shown. It is made by bonding 3 boards together, and there's a load applied. When that load is applied, the beam will deflect as shown. If these boards had not been bonded together, we would expect this behavior, where we see the boards are offset at the ends. If we consider the bonded beam again, we recognize that there must be a force that is being resisted by the glue or fasteners that are bonding these boards together. That force is a shear force, which is trying to cause the boards to slide against one another. That force is called shear flow. Here's a beam made of wood laminates that is being tested in bending, and we can see failure at the ends of the beam as a result of shear flow. This type of beam is called a built-up beam, and we can calculate the magnitude of the shear flow between the built-up sections of the beam. And we will use this equation, the shear flow equation, to do that. The shear flow equation is very similar to the shear formula. The difference is we are not calculating shear stress, we are calculating shear flow, which is given the symbol lowercase q. Also notice that the t that existed here in the shear formula is gone in this equation. For shear flow, the units are force per distance, such as newtons per meter or pounds per foot. V is the internal resultant shear force, which we can get from the shear diagram. I is the moment of inertia of the full cross-section about the axis perpendicular to the internal shear force. Q is equal to this expression here, y bar prime times a prime, and it is determined in a similar manner to what we discussed in the shear formula lesson. Let's consider 3 different built-up beams. In each of these built-up beams, the shear force is in the vertical direction. Now let's consider beam A. This section is composed of 2 members, and we can calculate the shear flow at the joint between these 2 members. And the 2 members are being held together by fasteners. And we want to know what the shear flow will be on this joint so we can calculate the capacity or spacing of the fasteners. A prime is the cross-sectional area of the segment that is connected to the beam at this juncture where the shear flow is going to be calculated. Y bar prime is then the distance, as always, from the neutral axis to the centroid of A prime. Beam B is composed of 3 parts, and we can see that there are 2 fasteners at a given cross-section, and we can calculate the shear flow on both of those fasteners. Considering the Q equation, we would use for our A prime area the shaded area here. The y bar prime would be the distance from the neutral axis to the centroid of A prime. In beam C, the cross-section is composed of 5 pieces. And for the top piece, if we wanted to evaluate shear flow at the joint that is connecting the top piece to the rest of the member, we would use for our A prime, the shaded area. Y bar prime would then be the distance from the centroid to the neutral axis. Another useful equation is the equation for spacing of fasteners. And that equation is shown here, where S is the longitudinal fastener spacing. That means it's in the direction of the long axis of the beam. And it's going to have units of length, such as meters or inches. C sub F is the capacity of a single fastener. And that's the shear capacity of the fastener, or the fastener's ability to withstand a shear force. N is the number of fasteners that are crossing the A prime boundary, and we'll look at that in the next slide. Small q is shear flow, as we calculate with the previous equation. For the 3 built-up beams that we looked at before, For beam A, we have one fastener crossing from our A prime area into the rest of the beam, so our N is equal to 1. In beam B, there are two fasteners crossing into the A prime area, so N is 2. And in beam C, there are three fasteners crossing through the A prime boundary, so N is equal to 3. Let's now consider an example problem that incorporates the two formulas we just discussed. This is a built-up beam composed of an I shape and two plates. And the problem says two 20mm thick plates are bolted to the top and bottom. If the internal resultant shear force V is equal to 300 kilonewtons and the bolt shear strength is 30 kilonewtons, determine the spacing S. We see that the spacing is in the longitudinal direction of the beam. The first step will be to calculate the moment of inertia for the full built-up section. This section is symmetrical about its neutral axis, and we can calculate the moment of inertia as the moment of inertia of a block that is drawn around the perimeter of the beam, and then subtracting off the interior blocks on either side of the beam web. And we can get a value for our moment of inertia as shown. Next, let's calculate a value for Q. Now, there are two plates being added to this beam, and because of the symmetry, we can assume correctly that the shear flow will be the same at both the top and bottom plates. So let's just consider one plate. We can take for our A prime area the area shown here in green. Y bar prime is then the distance from the green area to the neutral axis. And this is going to be equal to, our area is 0.2 meters wide by 0.02 meters tall, and Y bar prime is 0.16 meters. And here's the value for Q. Now we can calculate the shear flow that is occurring right at this joint between the plate and the top flange of the eye. Shear flow is equal to our internal resultant force, 300 kilonewtons, times our value for Q, divided by our value for moment of inertia. And we get a value of 624.4 kilonewtons per meter. What that means is for 1 meter of length in the longitudinal direction, we will accumulate 624.4 kilonewtons of force. And these bolts then must resist that force. So now we can calculate the spacing of the fasteners using this equation. C sub F is the fastener capacity in shear, and that was given to us in the problem statement, which is 30 kilonewtons per bolt. N is the number of bolts that crosses through our A prime area, and we see that the green area is our A prime, and we'll have 2 bolts passing through that area. So N is 2. Lowercase q is our shear flow. It is 624.4 kilonewtons per meter. And we can calculate our spacing to be 0.96 meters, which is 96 millimeters. And we're done.